Hello, everybody, and welcome back to another Mr. Farney Earth Science video. This is the third video in our volcano unit. And within this video, we're going to be talking about different types of volcanic eruptions, different things that are associated with the eruptions. We're going to speak a little bit about viscosity, what that is, and how that makes up different types of magma, how that kind of corresponds with different types of magma. We'll learn about 3 different types of magma in our class. And again, it's directly correlated to where that volcano is located, and the types of source material that makes it up. We'll look at things called Pahoehoe lava flows, Aha lava flows, and all that fun stuff kind of associated with them. So firstly, eruptions, all volcanoes, they erupt, even quiet ones, even when the little lava bubbling out of the surface of our quiet volcanoes, that's still technically an eruption. All eruptions and eruption material, it's generated by the magma. So before we get too deep in the weeds of the types of eruptions, let's play Chef Boyardee here for a second and learn exactly how magma is made. Firstly, you need high temperatures. It needs to be really, really hot, 800 to 1200 degrees Celsius, because remember, we need to melt down that rock material that's cycling its way back underneath the Earth's surface in order for that magma to start forming. So high temperatures and pressure, it has to form deep below the Earth's surface. You're not going to get very high temperatures near the Earth's surface where it's a lot cooler. It's got to be deep underground. What is magma made out of? Firstly, it's made out of different types of dissolved gases within the magma. The amount of dissolved gas is going to directly correlate to what the viscosity of that magma is. Both these things play into the explosivity of a volcano, but we'll get there in a second. What is viscosity? It's the resistance to flow. That's how scientists define it. If I'm looking at something and I'm trying to describe is viscosity, I'm going to be looking to see what it's comprised out of, and is it moving very quickly or is it not moving very quickly because of that material. So viscosity, it's the resistance to flow. You'll hear people describe things as something being highly viscous, have a low viscosity. What do we get a little more descriptions of those two? Well, if we have a cool magma, it's more viscous. It flows less. It's more solid. It's not going to be able to move as quickly. If you have something with a high silica content, that also contributes to it being more viscous. If it has more basalt content, it's less viscous. It flows easier. And some people can kind of get this concept confused, because if I hear that something is highly viscous, immediately I'm like, well, why isn't that, going faster? Why do I say highly viscous things flow slow? It's just how it's described. How do you remember this? Is a great mnemonic. If it's low, it will flow. Say it with me. If it's low, it will flow. If it has a low viscosity, it's going to flow fast with our different basalt lavas. If it's high viscosity, there's no rhyme there. If it's highly viscous, it's not going to flow. So if it's low, it will flow. That's a good way of remembering viscosity. We also have a chart here to kind of help out with viscosity. These are 3 different main types of magma that we're going to concern ourselves with within our class. We have basaltic magma, andesitic magma, and rhyolitic magma. When we go and talk about igneous rocks, when we get to kind of mineralogy and things like that within our class, we'll look a little more at basalt, we'll look more at andesite, we'll look more at rhyolite. For now, we're just recognizing that basaltic, andesitic, and rhyolitic are 3 different types of magma. Looking at basaltic, it has a low viscosity, so it's going to flow. If it's low, it'll flow. There's a low viscosity. The amount of silica that's in it is low as well. And these are associated with quiet eruptions. Remember, a basaltic, that's coming from our upper mantle. We're going to see that at our ocean ridges, at our hot spots like in Hawaii. This is not going to be very explosive of a volcano. The middle one, andesitic, has kind of a middle ground viscosity because it has a middle amount of silica, okay? It's coming from our oceanic crust. So we're going to find andesite or andesitic magma around areas where we have our subduction zones going on. Because we have kind of that middle ground viscosity, it's going to take more oomph to get it out of the volcano. So we're going to have this associated with volcanoes that have moderate eruptions associated with it. Rhyolitic magma, It has the highest viscosity. It's moving slowest. So since this has a high viscosity, it's not moving very quickly. It's going to take a lot of effort for it to kind of erupt out of the volcano. That's why the types of eruptions from this are highly explosive. These are composite mountains primarily. And in the source material for rhyolitic magma is our continental crust. So 3 different types of magma, 3 different types of viscosities. This is a great chart to help you kind of break down the differences between the two. Now we can get more in depth if we wanted to about, the percentage amount of silica in each of these magmas, but we're not going to concern ourselves with that right now. We can just, go off of the low, intermediate, and high levels, and that's perfectly fine for the nature of our class. Types of eruptions, quiet eruptions. We have low viscosity magma. This is our basaltic magma. This is where the lava is going to ooze out of the vent of the volcano. I always love that word ooze. It's a good descriptor word. It's oozing out of the vent of our volcanoes, whether it's our hot spots in Hawaii, like we might see here on the picture on the right, or if we're deep under the ocean, in the ocean, at our ocean ridges, we're going to have these long elongated blobs of lava breaking out of the skin of our kind of basalt rock material that's formed there. We see that, we call them pillow basalts. They're kind of like oblong shapes of rocks that kind of resemble pillows, but they're basalt rocks and they form that kind of circular pillow-like shape deep underwater because of the rapid cooling once that lava reaches the ocean water. Quiet eruptions, low viscosity magma. We're talking the basaltic magma. We have evidence of these types of basalt flows on the moon. In our Marias right here, the dark sections on the moon, that's our basalt regions. Evidence of ancient seas on the moon. That tells me if there's basalt flows there, there was probably some sort of convection or tectonic activity occurring on the moon sometime in the past. It's no longer tectonically active, but we have these evidence of these ancient seas that might have existed on the moon sometime in the past, probably relatively close to when it kind of broke away from Earth during the Hayden collision events that were occurring some 4.5 or older billion years ago in Earth's history. So we have evidence of that on our moon. There's evidence of volcanic activity other places on other moons like Mercury, Venus, Mars, and Jupiter's moon Io. All of these places have tectonic activity, and it's very similar mechanisms to that we have on Earth. So if we know the types of volcanoes that are in these places, like if we see a composite volcano, we could glean, okay, maybe they have rhyolitic-like magma in those places. So we can get a lot of information using Earth as kind of our source material and be able to kind of project it onto other rock surfaces or other areas of volcanism within our own system and get a kind of better idea of what's going on with our astrological neighbors. So I think that's really cool. If you want to read more about that, here's some links that you can access through our Google Slides on our classroom page. If we're going to talk explosive eruptions, we want that highly viscous magma. Remember, this is magma that's not going to go anywhere easily. Generally what happens, this magma clogs the vent of the volcano, pressure builds behind it over time, and then eventually that cork, it's going to pop right off the top of the volcano. If it's clogged for a long period of time, that magma is going to search for weak points. That's what happened with Mount St. Helens in 1980. The vent got clogged, and then it found a weak point out the side of the mountain and erupted sideways out of Mount St. Helens. That's what happened there. Generally associated with explosive eruptions, you'll have massive ash clouds, but you'll also have this thing I highlighted in orange here. This, in my opinion, is the most dangerous part of explosive eruptions from composite volcanoes, is our pyroclastic flow. It's this turbulent blend of different types of really hot, molten, finely grained material mixed with highly temperature gases that move incredibly fast over landscapes, sometimes 300 miles an hour or faster. In the town of St. Pierre in 1902, one of these pyroclastic flows came flying through when their volcano erupted, and it engulfed everything, incinerating everything in its path, including 30,000 people. So the pyroclastic flow This is extremely dangerous. Mount Vesuvius in Pompeii. Unfortunately, all those people that got buried and almost instantly kind of cocooned and mummified underneath that volcanic ash, it was the pyroclastic flow that did that, that consumed the entire city of Pompeii and its people with it. So pyroclastic flow, very dangerous. The second most dangerous thing I would say with the volcano is the lahar. If your volcano erupts and it's kind of near glaciers or a lot of snow material, that snow can melt very quickly. It can have a lot of excess water then running down the mountain, triggering mudslides. But here's the thing. Yes, I know it's glaciers and glaciers are cold, but it's a volcanic eruption. The lava coming out of the volcano is very, very hot. Remember, in order to make magma, it has to be hundreds of degrees Celsius hot. That's going to heat up that glacier water. That glacier water is going to mix with mud and create these lahar slides, which are destructive debris flows coming down the slopes of the volcano. Even though it is kind of mud mixed with water, there's still a lot of volcanic ash and debris mixed in there. Temperatures for this can be well over 100 degrees. That's really hot mud flow flying down the mountain. It's going to grab everything getting in its way, and it's extraordinarily dangerous. So again, the things that are most dangerous from a volcano generally are the things that move the fastest from it. Our pyroclastic flow moves very quickly. Our lahars move very quickly. Yes, the projectiles coming up out of the volcano, especially our composite explosive volcanoes, are very dangerous, but I would rank pyroclastic flows and lahars above those two things, and then the lava flow that's associated with it is actually way down the totem pole. So that's just my opinion of how you would want to go about ranking the destructive nature of these things associated with explosive eruptions. If you want to read more about explosive eruptions, there are links to different videos and images here that you can find from Krakatoa. We have images from Pompeii that you can look up to. So I encourage anybody in my class to find these links on our slides and explore them more on your own time. Lastly, we're going to look at two types of lava flows that come out of some volcanoes. First, we have the Pahoehoe lava flows, where we have a lot more gas. This is more fluid. It's relatively thick, yet it's kind of fast. It's made out of that ballistic lava, so it has a low viscosity, so it's going to flow. There's that low silica content within it. It's made out of that oceanic crust, not oceanic crust. It's made out of that material. If we slide back a bunch of slides to our table, material from our upper mantle. So it's going to be able to flow very easily compared to other flows. Here's a picture of it on the right. It's a creeper, this one. It moves kind of quick, but it depends on the type of flow, whether or not you're going to get it. I'm going to unmaximize here for a second, just to show a zoomed in video from Hawaii in 2018 of a Pahoehoe lava flow. I'm going to maximize it so it's easier to see. You can see here how it's not overly solid. It looks kind of like a squishy material that you might be able to describe as being somewhere partially between liquid and solid, but you can see how it's slowly rolling over top of itself as it's slowly making its way down the street here. This is what I would say something that's kind of has a low viscosity, maybe encroaching upon intermediate. You see how it kind of rolls over top itself. It kind of looks like a very, very slow moving river. This is a Pahoehoe lava flow right here. There's nothing you can do to stop this. It's going to kind of engulf everything because the temperatures for this lava flow are very, very, very hot. This person is standing about 20, 30 feet away from it. And he's using his camera to zoom in. And he says where he's standing, he feels the heat radiating from this. And he says it feels like it's easily over 120 degrees from where he's standing. So this is very hot, slow moving lava. This Pahoehoe lava flow. Okay. The last type of lava flow that we're going to concern ourselves with for today, after we get past the Pahoehoe, is the lava flow. This contains little gas. It's very slow moving. It's highly viscous. It can be anywhere from 3 to 10 meters thick. So it could be upwards of 30 feet. And it moves very, very slowly. It's sometimes described to be about as slow as a turtle. moves on the ground. So we have another video to show this type of lava flow. So remember what the Pahoehoe looked like, and this is what the Pahoehoe lava flow looks like. It's very much thicker, it's larger, it's moving slower. And since there's less gas content within it, it's going to be a lot more angular. It looks more like rocks, just kind of moving in engulfing areas. This is our Pahoehoe lava flow. So we can see, depending the type of magma that we're dealing with here, the type of gases that are in it and dissolved in it, we could have very slow moving lava like we have here with the Pahoehoe lava flow, or we could have that more liquidy looking lava flow that we have with the Pahoehoe. So this is really cool. See how it's kind of crumbling as it is advancing forward. Again, the cameraman said temperature is still very, very hot where he's standing about 20 feet away from it. He says that it does still feel about 120 degrees where he's standing. So if you see this creeping towards you, and it's a creeper, I would definitely get out of its path because you're not going to be able to stop this. It's going to engulf anything that kind of gets in its way. So that's a good stopping point right there. That's all the things that we covered about different types of eruptions, the 3 different types of magma, our basaltic magma, and acidic magma, and rhyolitic magma, viscosity, high, medium, low, and the types of source material that's associated with it. So please, if you have any questions, go ahead, let me know. And I'm just going to leave you with this last slide right here that gives you just a little bit of more information about determining whether or not eruptions are going to be explosive or relatively quiet. Again, has to do with the amount of gas and the amount of silica content that's in the lava or the viscosity. So have a good rest of your day. I'll see you next time where we're going to talk about different types of intrusive structures that are found near volcanoes underground. So have a good rest of your day. We'll check you out next time. Bye-bye.